Good afternoon, everyone. Thank you for joining this AGU webinar. My name is Rob Rader. I'm the Director of Engagement and Membership here at AGU, work very closely with our sections. And one of our awesome sections are sponsoring this webinar today. It's the Global Environmental Change section. And so I'm going to go ahead and introduce the president of that section, and he's going to go ahead and introduce today's speaker. So Phil Mote is the president of Global Environmental Change, and he's here. Thanks for joining, Phil, and you go ahead and introduce our speaker today.
Thanks, Rob, and thanks everyone for joining, and thanks Johan Rao for working with Claire to set up this webinar. This is part of how our section is marking AGU's centennial. We have 4 webinars during the course of this year. We had 2 in May, one on drought and water security in the West by Jonathan Overpeck, then Climate Extremes by Sonia Senevirantne, also in May. And then in November, we'll have one by Julie Silva on climate change and inequality, distributional impacts and dynamic vulnerabilities. All of these webinars are available at webinars.agu.org. The recordings are available, including the one for today. I'm very pleased to be able to introduce one of our AGU fellows from 2016. Claire Parkinson has been a climatologist at NASA's Goddard Space Flight Center since July 1978 and a senior fellow there since 2005. She's been the project scientist for the Aqua satellite mission since 1993. It's my very great pleasure to introduce her to talk about climate findings from a 40-year satellite record of Arctic and Antarctic sea ice. Claire.
Okay, Phil, thanks a whole lot. So first off, if anyone doesn't know what sea ice is ice that's frozen seawater, and it's not an iceberg. Icebergs come from land ice instead. So sea ice is frozen seawater. It tends to be fairly thin, like 4 meters would be a thick sea ice flow. However, even though it's fairly thin, you can land a helicopter on it or a regular plane. So as long as it's a couple of meters thick, it's pretty steady. So this shows the distribution of sea ice in midwinter and midsummer in the Arctic. And these are averages over the 40 years, 1979 to 2018. And the black circle in the middle is simply the region near the pole where the satellite did not get close enough to the pole to get the data filled in there. So that's the only reason for the black there. And the numbers being plotted are what's called sea ice concentrations, and that refers to the percentage of each pixel area that has sea ice versus the open water. So if a pixel, which in our case is roughly 25 kilometers by 25 kilometers, if a pixel is entirely covered by sea ice, then it's 100% concentration. If it's got no sea ice, then it's 0%. If it's half filled with sea ice, it's 50%. So that's what sea ice concentration means. And in February, the ice extends to about 15 million square kilometers. The area of the US is 9.8 million square kilometers. So the sea ice area in midwinter is a little more than 1.5 times the area of the United States. That illustrates why the satellites are so important. The area of sea ice coverage is great enough that there's just no way that we could really have a good record of the entire area day after day after day by any means other than satellite data, especially since nobody lives on the sea ice. People might be there temporarily, but nobody lives there. And even if you tried to put a station there, the ice moves around, so that station would be moving around too. So the satellites are critically important to us to get a record. And then August in midsummer, it's much less than half of what the aerial coverage is in winter. And here's the picture for a similar picture for midsummer and midwinter in the Antarctic. And here again, the difference between summer and winter is huge in terms of sea ice coverage. Of course, in the Antarctic, the summer is February and midwinter is August. So huge contrast between how much ice you've got in the summertime versus the wintertime. But in both the northern and the southern hemispheres, the amount of ice, especially in wintertime, is very large. In the Antarctic, it's about 18 million square kilometers, so even more extensive an ice cover than the wintertime in the Arctic. So with this huge coverage and the fact that the sea ice really does matter, NASA naturally wants to get a record of the sea ice. So here's an illustration of one of the really important reasons why sea ice matters. And that's because the ice is a white surface. Most of the solar radiation that's incident on it gets reflected back to space. If the ice leaves and instead the solar radiation is incident on the liquid ocean, then most of that radiation goes into the ocean, gets absorbed in the ocean, stays within the Earth atmosphere system, and therefore contributes to the energy of the system and warming of the system. So the feedback illustrated in the right schematic here would be, if the system is warming, then you expect a reduction of sea ice because it's warming, and therefore less sea ice is going to be formed and more sea ice is going to melt. But because of less sea ice, the surface reflectivity is going to go down, because instead of the highly reflective ice, you've got the far less reflective ocean. Therefore, you've got more absorption of solar radiation within the system, and therefore the system warms even more. So a positive feedback, or you could call it an enhancing feedback, because positive sounds like good, and this is really not a good thing to have a positive feedback like this. So that's one of the very important reasons why sea ice is important. And this slide shows some other reasons for the importance of sea ice. Sea ice is a fairly strong insulator, restricting the exchanges of heat, mass, and momentum between the ocean underlying the sea ice and the atmosphere above. The sea ice also has a lot of impacts on plant and animal life. The animals that are most often talked about would be polar bears in the Arctic and penguins in the Antarctic, but there are lots of other animals that are also impacted by the sea ice, including seals and walruses and Arctic foxes and a whole slew of animals and plants that are affected. And sea ice does impact human activities. Certainly, it makes it more dangerous for ships in the vicinity, but it also is a platform that humans can walk on if that's what they're wanting to do. So it impacts humans as well as other life forms. So NASA, when it started getting satellite data down in the 60s and the 70s, sea ice was one of the many things that NASA scientists were trying to figure out. How can we use the satellite data to inform the world about the sea ice cover in the Arctic and the Antarctic? On the left here, it's clear that from satellite, from in particular Landsat visible imagery, you can see sea ice really well, just like you'd be able to see it if you were in a plane flying over, in this case, the area is the Weddell Sea, which is a sea right adjacent to Antarctica. So you can see it really well. This is great. But the right picture then shows the limitations of the visible data. And that includes the fact that if there's a cloud in the way, just like if you were in an airplane looking down, if there's a cloud in the way, you see the cloud and not what's at the surface. And the same thing with an instrument that's measuring visible radiation from space. So that's an issue with visible data. Another issue would be if it's dark out. And in the Arctic, it's dark out for months at a time. So if we were using visible data, we couldn't get data through much of the middle part of the winter. So we don't tend to use visible data for our climate records. Instead, we go with microwave data. And the microwaves have the huge advantage of, if you pick the right channel of microwave radiation, the microwaves can go straight through the clouds. And this is great because that means you're essentially able to see through the clouds by using the microwave data. And then the other big plus is that the microwaves are predominantly coming from within the Earth system. They are not coming from the sun and getting reflected off. So it really doesn't matter whether it's dark out or light out because the light's not coming from the sun. So for those huge reasons, we tend to use the microwave data for our long-term climate records. And this is what the microwave data looked like back in the 1970s when we started putting together a long-term record. And all the black indicates missing data. Now, this was an instrument, the electrically scanning microwave radiometer that was on the Nimbus 5 satellite, which was launched in December of 1972. It obtained a 4-year record of data that for most of the 4 years, we got reasonably good pictures for once we averaged to monthly averages. Some months were missing data altogether, but this was a proof of concept instrument, this ESMA on the Nimbus 5 satellite. And it was phenomenally successful in terms of proving the concept that microwaves would be valuable in terms of looking at lots of different features in the Earth system. The feature I was looking at and the team I was with was looking at was the sea ice cover, but other people here at NASA Goddard Space Flight Center were looking at other aspects like vegetation and precipitation and sea surface temperature, and they were also finding that the microwave data ended up being really valuable to them as well. So, as I said, we tended to average up to monthly averages, and this is the cleaned up picture from September of 1973, where we've gotten a monthly average, and as you can see, it looks pretty good once you average a whole month, because then the missing data in some days would be canceled out by getting data in other days. So September 1973 looked quite reasonable. Now, look what happens for September of 1974, 75, and 76. There's this huge area of open water right toward the top of the picture. This is in the region called the Weddell Sea, so it's called the Weddell Polynya. Polynya is a Russian word for an area of open water within an ice cover. So this was huge, a huge area that had not been anticipated at all. So it was a big surprise when this huge area of open water showed up on these 4 late winter pictures from the Antarctic. So lots of scientists tried to figure out what could conceivably be causing it. And certainly the scientific view is that likely it's something oceanographic, maybe the atmospheric winds. The other perspective from a tabloid, The Globe, has an entirely different perspective on this. And the headline in The Globe, UFO base found under Antarctic ice. This is definitely not what the scientists thought, but it was very interesting. It was one of the extremely unusual cases where anything regarding sea ice showed up of interest in the popular press way back at this time in the early 1980s. And it is one of our images of ice. At that time, very few people were interested in sea ice. Things have definitely changed in terms of that, and it is in substantial part because of the satellite data and what the satellite data have shown. But we at NASA Goddard went ahead with the Nimbus 5 passive microwave data, passive meaning that the instrument is not sending a signal down and receiving it back. Instead, it is simply receiving the radiation that's coming up. So we put together the data set for the 4-year data set for this instrument, the ESMER on Nimbus 5. And first we did an Antarctic book, and that was led by Dr. Jay Zwally. And then we turned to the Arctic, and we did a similar book for the Arctic, and that one was led by me. By that time, fortunately, other instruments had been launched. Another instrument in particular on the Nimbus 7 satellite, the Scanning Multi-Channel Microwave Radiometer, or SIMR, was launched in October of 1978. And since then, this type of instrument, passive microwave instrument, has continued to be taking data pretty consistently from that time of October 1978, late October 1978, up until the present. The Nimbus 7 SIMR instrument succeeded until August of 1987, but by the time it failed, the Defense Meteorological Satellite Program, DMSP, had launched a Special Sensor Microwave Imager, SSMI, in June of 1987. So there was a little overlap between those instruments, which was wonderful for us, although we would have liked a much longer overlap. And then subsequently, the DMSP program has launched more SSMIs, and then also an advanced version called an SSMI Sounder, or SSMIS, first launched in October of 2003. So we have a record that spans the period since the launch of the Nimbus 7 SIMR, and therefore it's almost 41 years now that we now have a record. And in the meantime, the Japanese launched, well, they have a satellite, the Advanced Microwave Scanning Radiometer for the Earth Observing System, AMSR-E, on NASA's Aqua spacecraft, which was launched in May of 2002. And then they also have a follow-on AMSR-2, which they launched on their own satellite, Suzuku, back in May of 2012. So we have these passive microwave instruments, a long record that so far is continuing, and we hope it will continue a long time into the future. So now we come up with the first poll question, and there are 2 poll questions. And so Rob, I'll turn it over to you to ask the poll question.
Sure thing. So the first poll question, let's see.
It's
Okay, I'll
which month
launch.
has the least amount of sea ice in the Arctic?
Okay, the poll is open. Got about 58% of the attendees have voted, 60. Just let me know when you want to close the poll, Claire. Do you want to wait for everyone to vote?
No, let's close it now. And I can't see what the results are. So can you tell me what the results are?
Yep, I just want to go ahead and make sure I capture them here. Okay, so let's go ahead and close the poll. Give people still voting, so. All right, I'm closing it now. So let's share the results.
Okay, 79% said September. Those 79% are correct. And the others all said either August or July, both of which would be reasonable guesses. I'm glad nobody guessed March or April. So this is great. So the 79% who said September, they're all correct. The ones who said July or August, you were probably thinking in terms of the hottest season. The hottest month tends to be July or August. However, the sea ice continues to retreat as long as the temperatures continue to be above the freezing point. And so that's why the sea ice minimum ends up later than the temperature maximum. So it ends up in September, and those 79% were correct. Okay, so now, these two figures were published in a paper by me and Don Cavalieri back in 1989. So this is when we had the Nimbus 5 data for the years 1973 to 76, with some months missing, and then the Nimbus 7 data from November of 1978 on. So we've never really been able to successfully merge the two. We've made some attempts, and we do have some publications on it with other data in between those two, the Nimbus 5 and the Nimbus 7. But most of our data record starts with the Nimbus 7 data starting in November of 1978. So, and sometimes we just start with January of 79 to get full years instead. But there was a little suggestion in this paper by me and Don that the data from the simmer on Nimbus 7 were showing a very slight decrease. This was not a convincing decrease over those years of the simmer data, but it was such that we felt like it's necessary for us to go to the effort of really putting together a coherent, good data set that continues on into the future, especially since by that time, late 1980s, we and others were thinking about the concerns being raised regarding global warming. So 10 years later, in 1999, the group of us here at Goddard, me and Don and Per Glorson and Joy Camiso and Jay Zwally, we ended up publishing a paper that now had more like an 18-year record, and it was much more definitive than the 1989 one, but this plot shows the monthly averages. And as you can see, if all you're seeing is the monthly averages, certainly what's most striking or apparent to the eye would be there's a lot more ice in the winter than in the summer. So we really wanted to be looking at what trends there are. So we removed the seasonal cycle in order to do that. And the way we removed it was we took for instance, the very first data point here is November of 1978. We took that value and we subtracted the average of all the Novembers. Then the next point, December of 1978, we took that value, subtracted the average of all the Decembers. And we went on throughout the entire record and we did that. And the result is what we call monthly deviations. And this plot shows what the monthly deviations look like. Now it is so much more apparent that the ice was decreasing. Now, it still wasn't entirely convincing, because if you note in 1996 here, there were some high values. And so it wasn't entirely convincing, but it certainly was more convincing than what we had back 10 years earlier. Now, to add to this satellite data showing that the ice was retreating, right the same year came out a paper by a group from the University of Washington, led by Drew Rothrock, showing from marine data that the Arctic sea ice was thinning. Now, they were using submarine data, which was bit by bit being released by the Navy as they declassified it. So they didn't have the full data set yet, but they sure showed that from the data they had, it was thinning. Later, they had a more complete data set for the same years, and they showed that it wasn't thinning as much as they had thought, but it was thinning. So the combination of these two in 1999, you've got the satellite data indicating a retreat of the ice, and the submarine data indicating a thinning of the ice. And these two, combined with the fact that by 1999, computers were so much more capable, people had computers on their desks, and the data were so much more readily available through data centers, especially the National Snow and Ice Data Center, NSIDC in Boulder. All those things combined to making the sea ice data used and looked at by far, far, far more people than was the case back in the 1970s. So here's just a picture to show that we do sometimes get out on the ice. And here we flew most of the way, but for the last couple of miles, we hooked up with the dog sled team in order to get exactly to the North Pole. Because with a plane, you land where the flow is solid enough for you to land. With a dog sled, you've got much more flexibility and where you can go. So we hooked up with the dog sled to get to the exact North Pole, and we took thickness measurements. We did find some ice that was thicker than 4 meters, which was nice because we know the ice is thinning and that not a whole lot of 4 meter or thicker ice is around anymore. But with the results from the submarine data showing thinning, the satellite data showing a retreat of the ice, sea ice has become essentially a poster child for global warming now. So sea ice is far more in the limelight than it had been way back in the 1970s and 1980s. And here's what the record looks like for the for the 40-year plus record from November of 1978 on until the end of last year. Now, when you look at the monthly averages, you don't even need monthly deviations to be able to just see immediately that the sea ice cover is decreasing. We do still calculate the monthly deviations and plot them as shown here on the left. And we also calculate and plot yearly averages as shown on the right. And these come out to decreases of about 54,000 square kilometers a year. And to put that in perspective, that's a little bit larger than the area of Costa Rica, or a little bit larger than the combined area of Massachusetts and Vermont. So that's how much is being lost each year on average over the span of this 40-year record. If you look at these plots, you'll see that 2 years in particular, especially on the left-hand plot, it really shows it well. 2 years in particular had really huge decreases in the sea ice cover, and those were 2007 and 2012. 2007 was the biggest shock to us because we had never seen anything like that in the sea ice record before. So when it plummeted that much, there were some people who were saying we might have an ice-free Arctic within a decade. Now that didn't happen, but you can see with the plummeting there in the 2007, you can see why some people might have started guessing that it might just continue plummeting in that way. Fortunately, it didn't. It rebounded a bit over the next few years, but then in 2012, it went down even further than it had in 2007. And so far, 2012 remains the record low. So those two, 2007 and 2012, were the record lows. And here I show images of the Arctic sea ice cover in these two cases, the 2007 case at its minimum and the 2012 case on the right in its minimum. You can see on the left-hand picture, the 2007 one, you can see that there's a really clear, easy northwest passage up north of Canada. So there'd be an easy northwest passage. The northeast passage on the left side would be a little more difficult because there is a little area where it would be blocked by ice. Then if you look at 2012, you see there the northeast passage would have been just a breeze to sail through the northeast passage north of Russia, because there is a large amount of open water there. We do get updated information on our website each week, and the website is neptune.gsfc.nasa.gov. And this shows the updated, so it shows up until Sunday, so 3 days ago. So up through October 20th, it shows what the Arctic sea ice extent was. And on that date, October 20th, it was a record for that time of year. So it is October 20th, the lowest value we've seen on that date of the year is this year, and at 6.1 million square kilometers. Now, there's also many other things we can look at from the data instead of just the ice extent. And one of the things that I've looked at is the length of the sea ice season. And what this means is how many days a year at the individual pixel area. And again, a pixel is roughly 25 kilometers by 25 kilometers. So for each pixel area, for each year, simply count how many days a year had ice. And the limit being used here would be if it's 15% or more ice coverage, ice concentration, then it's included in this calculation of how many days a year have ice. So the left-hand one was with the Nimbus 7 data, and that satellite did not get anywhere near as close to the pole as the 2013 satellite, which is one of the Department of Defense's satellites. So they got a lot closer to the pole. So that's why the black circle in the middle is much greater on the left than on the right. But if you look at these two, you could easily see that there's the length of the sea ice season is longer for much of the area of the Arctic in 1979 than in 2013. And the reason it's 2013 here is that this figure was adapted from a publication from 2014. However, I also take each point and look at its length of the sea ice season throughout the record. And then I plot the trend. So take each point and then do a linear least squares fit through that one point's data. And when I do that for the first 10 years of the record, 1979 to 1988, the picture here shows the results. And it shows that in general, in the Western Hemisphere, the length of the sea ice season was getting somewhat larger. In the Eastern Hemisphere, predominantly, it was getting lower. But there was a lot getting a longer season and a lot getting a shorter season. Then with the 20-year record going from 79 to 98, now it's much less getting longer seasons, and it's much more clear that predominantly it's getting shorter seasons. Now the white area in the middle, the white just means it's not changing, and that's because that's essentially the area of full ice coverage. So it's 365 days a year, each day of each year throughout the record. So, and that's why it's white. So, but then you go to the 30-year record, now taking it up to 2008, and you can see that now there's almost no area left with the season lengthening. It's almost all either staying put or shortening. And if you go to the 40-year record, it's even more extreme than what we see there with the 30-year record. So this is just one other illustration of what we can do with the satellite data and how the satellite data are showing a reduction in sea ice coverage in the Arctic. Now, other people also look at things like the age of the ice and how much older ice we've got left, and that those numbers are going down also. So in the Arctic, definitely from the satellite data, we are showing a reduction in sea ice, and that comes through with a number of different variables about the sea ice cover. It's also a part of a much larger selection of changes that are happening in the Arctic, all consistent. The ocean's warming, the atmosphere is warming, sea ice is decreasing, land ice is decreasing, shorter snow seasons, permafrost is thawing, growing season is getting longer, which is a plus, and increased primary productivity and increased erosion. The erosion increasing that's direct result of less sea ice, because if sea ice isn't right there up against the coast, there's much more chance for erosion to be occurring. So a consistent pattern is going on in the Arctic. I will soon shift to the Antarctic, and you'll see that it's not as consistent or as expected. But one more slide on the Arctic, and that's looking at the possible fact that there's an extension of the sea ice impacts beyond the polar regions. On the left here, on the left shows a model calculation, and this was done with a study that was led by David Rind back in 1995. I was involved, Doug Martinson was involved, and Rick Healy, so the four of us. And the red curve shows the results of the warming calculated for a doubling of CO2 by the model, the climate model of the Goddard Institute for Space Studies, the GISS climate model. So that's what the red shows. And it shows enhanced warming in the polar regions, referring to polar amplification of the warming. The blue line shows what happens to the calculations if you don't allow sea ice, the sea ice annual cycle to change. So it removes the sea ice calculations, and then you get a whole lot less warming. So it goes down to quite a bit less, all exclusively based on the removal of sea ice from the calculations. On the right is an observational picture from the atmospheric infrared sounder on the Aqua satellite, showing the polar vortex descent over the eastern US back in January of this year. And people tie the fact of likely more frequent occurrences of this type of situation because of changes in the ice cover. And I refer you on that to papers by Jennifer Francis from Rutgers and others. So impacts of the sea ice beyond the polar regions. So now turning to the Antarctic. And here's the summer and the winter images for the Antarctic. Again, ice concentrations. And here's the next poll question. Is the amplitude of the annual cycle of sea ice extents in the Arctic greater than the same amplitude in the Arctic? So that's just a yes or no or not sure answers.
Nope, the poll is launched and ready for responses.
Okay. And this will be the last poll. And I guess we should close it because we're going to be running out of time.
Okay. Thanks to everyone that has responded. We're closing the poll. And there are the results.
Okay, this is interesting. Okay, so this is much more evenly balanced. Now it turns out the ones who said yes, that it's greater in the Antarctic, that 39% are correct. So now, but it's, yeah, so Rob, if we could go back to my slides now. So, okay, here's, and now they're not advancing. Okay, so here's a picture of the Antarctic sea ice extents, monthly averages. And as you'll see in the summertime, it's way down at more like 3 million square kilometers. In the winter, it's way up at more like 18 million square kilometers. So in the Arctic case, it had been closer to like between 5 and 15. In the Antarctic case, it's between 3 and 18. So the Antarctic has the bigger amplitude, and part of the reason is the geography of the two. And if there's time at the end, I can go into that. But first, I want to show, once we take the seasonal cycle out of the Antarctic case, this is what we get. Monthly deviations on the left, yearly averages on the right. And here you can see that overall the trend has been positive rather than the expected negative trend. So, and you can also see that there was a huge change after 2014. So the positive trend was up through 2014, and then a huge decrease. So that the trend line values that I show within the plots, about 11,000 square kilometers per year, are much less than if you stopped the calculations at 2014, and those values are down lower on the plot, on the illustration. So those values are roughly double for up through 2014 versus up through 2018. So huge decrease. And this is true also not just for the yearly averages, but for every single month of the year. This shows the trends when you take the whole 40-year period, 1979 to 2018, each month. Each month is a positive trend, although November is real close to zero, so it's certainly not statistically significant on that one. But the black line here is what the trends looked like when the record only went through 2014. So much stronger trends before this huge decrease came in from 2014 on. Here shows the updated, we update both the Arctic and the Antarctic in the same way on the same website. And then here shows regionally. In the Antarctic case, the regions are not all acting the same. And the one that's really acting most differently from the others is the Bellingshausen-Amundsen seas. So the Bellingshausen-Amundsen seas, instead of showing the increases up until 2014 and then decreases, they were predominantly decreasing for much of this record of the 40-year sea ice record. You can see with every region, there's a lot of interannual variability, but in terms of the overall, the Bellingshausen-Amundsen seas were the ones that were unusual versus the others. And now the right hand, the plot on the right here is the trends and the length of the sea ice season in the Antarctic. And you can see that the Bellingshausen-Amundsen seas areas indeed have shortening sea ice seasons, whereas most of the rest of the way around the Antarctic has lengthening seasons. Naturally, because of how unexpected the increases were, a lot of scientists have tried to explain the increases, and up until 2014, when it was still increasing, there had been quite a few papers written that try to explain why the Antarctic sea ice was increasing. And some tie it to the ozone hole, some tie it to El Nino Southern Oscillation, some disagree with the ozone hole as a cause, others tie it to the Amundsen Sea, others to basal meltwater, and then others discount basal meltwater, and others tie it to the interdecadal Pacific Oscillation. And so there are a lot of attempted explanations. Clearly with the new data, all of these attempted explanations, it's reasonable to now relook at each of them with the new data showing the huge decrease after 2014. And there are people who have tried to explain the huge decrease. And this sort of shows just how big that decrease was in terms of, in terms of the yearly averages, it went from a record high for the 40 years of 12.8 million square kilometers in 2014, all the way down to the 40-year record low of 10.7 million square kilometers in 2017. That difference of 2.1 million square kilometers happened in just 3 years in the Antarctic. It took over 3 decades for the Arctic to lose that much ice in terms of the yearly averages. So gigantic decrease happened. And there are attempts to explain the decreases. And my main object is to show what the decreases are and others have tried to explain them, but it will be a while before there's any consensus view, because definitely so far there is not a consensus. And this just shows the just how extreme that 4-year period was in terms of the Arctic never had any slope for a 4-year period anywhere as close to as large in magnitude as what the Antarctic had from 2014 to 2017. So last slide here is before, I do have a list of references, but here's a summary slide, and just wanted to say sea ice is really important for many reasons, including that it reflects a lot of solar radiation. The satellites have provided us with a record of the entire sea ice cover that simply could not have been obtained feasibly with any means other than satellites. The satellite record has shown that Arctic sea ice has decreased quite a bit over this 40-year record. The Antarctic sea ice was increasing until 2014, then decreased quite rapidly. And there's a lot of ongoing work to try to explain the various things that we don't understand yet. So with that, I close.
Thank you, Claire. Appreciate it. So we are going to spend the next 8 or 10 minutes answering any questions that you all may have. You can ask your question by typing it into the questions part of your dashboard, or you can feel free to raise your hand virtually. And if you've got a mic or if you're on the phone, we can actually unmute you so you can ask your question directly of Dr. Parkinson. Give it a couple minutes for folks to get their questions together. All right, so we do have a hand raised here. Let's get that. Where'd it go? Okay, Jim, I'm going to go ahead and unmute you so you can ask your question. Go ahead, Jim.
This has little to do with what you're talking about, but what is the salinity of sea ice?
The salinity of sea ice is a lot lower than the salinity of water, liquid seawater. It varies. So as the ice ages, more and more of the salt content sinks down and goes into the ocean. So in general, the older the ice is, the less the salinity is. But this isn't always the case, because sometimes there might be water that sloshes up onto the ice and then it introduces the salinity again. So it's a whole lot less than seawater, but it's still salty. So it's still not palatable to drink.
And it's not as solid, I'm sure.
Pardon?
And it's not as solid.
Oh,
it would
right.
be.
All right, thank you, Jim. Appreciate the question. Going to go ahead and read a question that came in. So let's see, from Robert Curran. Did the huge Antarctic polynya seen by Nimbus 5 SMMR disappear?
Yes, in terms of it never reappeared. So during the years that the polynya was there, and it was actually the ESMR years, the Nimbus 5 ESMR, and during those 3 years, 74, 5, and 6, it was there the entire winter season. And then as the ice cover decayed in spring and summer, then the polynya disappears. So the polynya is gone at the end of the decay season in each case. But then it reappeared moved over somewhat to the west from 73 to 74, I mean 74 to 75 and 75 to 76. And then we have never seen a similarly sized area of open water in the Riddell area since then, in the middle of winter. So there have been some indications that there have been like other smaller polynyas, but nothing still of that magnitude. Back when the only record was the 4 years, 73, 4, 5, and 6, people were thinking it must be common since it's in 3 out of the 4 years, but then it's never reappeared. Rob, if there
Rob, I think you're muted.
Sorry, I am muted.
Oh,
Thank
okay.
you. Thank you, Claire. So Sarah, go ahead. I've unmuted you so you can ask your question. Sarah Farhan, are you on a mic or a headset? Sorry, Sarah, unfortunately we can't currently hear you. So if you want to go ahead and ask your question in the questions pane, we can go ahead and ask it for you. I do have another hand raised. Glenn Rudebush, hopefully I pronounced that correctly. Glenn, go ahead and ask your question on the mic. Glenn, can you hear me? Sorry, Glenn, if you're speaking, unfortunately we can't hear you. So if you want to go ahead and use the questions module, we can ask Claire your question for you. All right, we do have a few other questions coming in here, so I'll go ahead and ask these, Claire, and then we may need to end within a minute or two. From Darby, how do you see the future of sea ice observing satellites evolving or changing, i.e. with ICESat-2's data being released earlier this year? What would you like to see in the future sea ice observing missions?
Well, I would definitely like to have the passive microwave data set continued indefinitely. So I hope that we can continue with passive microwave observations. The ICESat-2 is wonderful in terms of hopefully it's going to get us a good record of the ice thickness. ICESat-2 was launched back a year ago in September of 2018, and the measurements hopefully will, it's ICESat-2, for those who aren't familiar with it, it has a laser altimeter on board. So it sends a signal down, receives it back, figures out how far below the satellite the surface is, and in that way enables a measurement of the topography of whatever it is it's looking at, vegetation, and particularly the ice sheets, Greenland and Antarctica, but also sea ice. So we hope that ICESat-2, the laser altimetry, will be able to get us a good record of the thickness of the ice, and they're also Cryosat to uses a radar altimeter to get the ice thicknesses. So hopefully both the passive microwave and the laser altimetry and radar altimetry will continue and get long-term data records.
All right, thanks for that question, Darby. From Cynthia, curious what you think will happen to the sea surface salinity and primary productivity in the SO during this drastic decrease starting in 2014.
Okay, I am definitely not a sea surface salinity expert, but with major decreases in sea ice, it does add somewhat less salty water, and so it should be contributing to slight decreases. And the ocean is so much deeper than the sea ice is thick, so it might not have a huge noticeable impact on it, but the impact of the decreased sea ice, meaning that that sea ice melts into the ocean, and melting into the ocean somewhat less salty water would indicate a slight reduction in salinity temporarily.
Thank you for your question, Cynthia. I think we've got time for maybe one more question. I apologize. So from Farah Akhtar, we've got, here we go. You commented on thickness of sea. Do you have comments about current thickness measurements and if they confirm the trends in sea ice extent that you recorded?
You broke up in terms of, could you read the question again? Because it came through kind of broken.
Sure. Can you hear me right now?
Yes, I can.
Okay. You commented on the thickness of sea ice measurements around 1998. Do you have comments about current thickness measurements and if they confirm the trends in sea ice extent that you recorded?
Yes, they do. And the current sea ice thicknesses would be the ones from the, well, Cryosat to IceSat to, and there are measurements from IceBridge, which is an aircraft mission that's bridging between the IceSat satellite and the IceSat-2 satellite. So those measurements do show thickness less than what the thickness measurements had been before. So it does seem that it's continuing to thin, that the ice is continuing to thin.
Thank you, Claire. So unfortunately, we've run out of time. We need to end today's webinar, but I want to thank Claire Parkinson for being part of this presentation. Really appreciate you taking the time to present to us, Claire. And I want to thank the GEC leadership as well for helping to coordinate these Centennial webinars. There will be a few more of them coming, so keep an eye out for them. I did put some links into the chat so that you all can find those, but they'll be on the learning area of the AGU website. As we continue to build out our new site, you'll start to see more and more of these. So, Phil, did you want to say one more thing before we go ahead and end the webinar for the attendees?
I just want, I'd like to thank you, Rob, for taking care of all the logistics here, and so that's very much appreciated. And I also want to thank Geck and Johan and everybody who attended. Thank you.
That's all I wanted to say. So, yep. Thank you, everybody.
Thank you, Phil. We'll see you all in a little under 7 weeks, I think. So thanks, everyone. Have a great day.
Bye.
Thank you.